Hello everyone, and there is one another solved problem which I'm going to discuss of set theory. If you look into this particular problem, here it is clearly mentioned there is a set which is given A which has certain members 1, 2, 3, 4, 5. So 3, 4 is a, I would say, smaller set within, which is a member of A than 1, 2, 3, 4, and 5. And which of the statement is correct or incorrect? Actually, this is what I need to mention. Now, if you see, there is a little differentiation which I need to understand. One is how many members are there in A. Members belong to the particular set. Set A contains 4 elements here. The first element is 1, which I have listed here. The second element is 2. Third element is a smaller set, 3, 4. And the fourth element is 5. So there are in total 4 members in the set. So cardinal number of A is 4. How many subsets A can have now? 2 raised to the power n, where n represents the cardinal number. So 2 raised to the power 4, that means total 16 subsets. Now, if you look into all these 16 subsets, what could be the possible subsets? I have listed them down here. And this collection of subsets belongs to the power set of A. And you can see another videos of mine on how the power set can be defined. This collection belongs to power set of A. You need to understand the difference between belongingness and subset. So if I write something like this, if I write this 1 as a subset, so these curly brackets say that 1 is a set. So 1 is a subset of A. That's a correct statement to make. But if I see this 1, it belongs to power set of A. That means it is a member of this family. But yes, it's a smaller part of A set. So this is the differentiation which you need to understand. And this is where you need to actually conclude, keep on concluding the things, right, about these statements. So first statement says 3, 4 is a subset of A. This is the incorrect statement. And why do you say so? Because 3, 4, if you see 3, 4 here, it's a member of A. So 3, 4 belongs to A is a correct statement. Perfectly fine. Now here if you see 3, 4 is further blocked into curly brackets, is telling you a singleton set. That means a singleton set which has an element 3, 4 as a set. Is it a subset of A? It's absolutely fine. It's correct. Look at this once again. I'll try to drop a Venn diagram here. This is how the AA looks like. A looks like this. 1, 2, 3, 4, and 5. 3, 4 is definitely a subset of A. There's no problem in it. So it's a correct statement. When I see fourth statement, 1 belongs to A. Yes, 1 is an element of A. I have already written it here. 1 belongs to A. 1 is a subset of A is an, if you, I think you can clearly figure it out. It's an incorrect statement. Why it is an incorrect statement? Because it is not even represented as a set. Every subset has to be represented as a set. Now if I see 1, 2, 5, so you can clearly see 1, 2, 5 here in this Venn diagram. They are clearly a subset of A, and that's a correct statement. Now if I see 1, 2, 5 belongs to A, what do you say about it? It's an incorrect statement. Because 1 to 5 actually, if you see here, 1 to 5 belongs to power set of A. That means 1 to 5 belongs to power set of A. That's a correct statement to make. A member. Same way, there are 2 more examples you can see. If you see 1, 2, 3, it's a subset of A. So you can clearly see 3 is actually in combination with 4. So it is not independently can be taken. So fundamentally 1, 2, 3 is a subset of A is an incorrect statement. 5 belongs to A is, if you see 5 belongs to A, what do you think about it? And 5 is a subset of A. There are 2 statements which are written here, and the third and last statement is phi as a set is a subset of A. So if I see all these statements, phi is a subset of A. Every null set is a subset of a set. Every null set is a subset of set. So this is the correct statement. There is no problem in it. Phi is a subset of A. Phi as a set. So this is a singleton set containing an element phi. This is an incorrect statement. Now again, if I have to see phi belongs to A, does phi belongs to A? Is it a member of A? See that once again. No, it's not a member of A. So it is again a incorrect statement here. Thank you very much. Hi everyone. In this video, I'm going to go with more practical examples of set theory and how the problems related to designing the subsets actually work. So let's understand some problems here, that how many subsets out of a set I can make. So I'll take some problems, and this concept you can read from previous lectures. You can study from previous lectures that a set can have 2 raised to the power n subsets. So I'm but repeating this concept, that number of subsets a set can have can be given by 2 raised to the power n, where n is cardinal number of the set. That means how many elements are there in the particular set. So let's take first example, and let us suppose if a set is given something like this, A, that how many subsets this set can have. A is equal to A. So it's a singleton set having one element. So if I look into its cardinal number, then n is equal to 1. So n is representing the cardinal number. It is equal to 1. So number of subsets it can have is 2 raised to the power n, which is actually 2 raised to the power 1, and that gives you 2 subsets it can have. Now, what are these 2 subsets? Here in this case, these subsets would be, first of all, a set is subset of itself, and phi, which is null set, is subset of every set. So this is another property, and all of these, collection of all the possible subsets of A comes under the power set of A, which can be represented by PA. So if I have to answer this question, that how many subsets this set can have, this set can have 2 subsets, and these subsets can be given by A and phi. Remember, I'm repeating this, null set, which is phi, is subset of every set, and the second thing you should remember is that every set, that means the whole complete set, is subset of itself. So doesn't matter how many subsets you are deriving out of a set, there will always be these 2 additional subsets which you need to add on. Let's take one more problem and it says if there is a set A and the number of elements given by AB. So if you look into the cardinal number of this set, the cardinal number is 2, and this set can have 2 raised to the power 2, that makes it 4 subsets. So 4 subsets it can have, it's clearly visible, it can have 4 subsets. Now what these 4 subsets are, first of all, let's start with that thing, every set is subset of itself. AB, phi, null set, is subset of itself. Then A, singleton set, is a subset of set A. B is another subset, which is a singleton subset, which is a subset of A, and all of this collection will come in the power set of A. So 4 subsets, 1, 2, 3, 4. Let's see a very interesting example. And this example says that how many elements power set of A will have or has, let's say, if A is equal to phi. That means A is null set. That means there is no element in it. Now again, how many elements of power set? So if I see, what do you mean by elements of power set? So if you see here, 1, 2, 3, 4, these 4 are elements of the power set of A. So here he is saying that A is empty. That means configuration of A is something like this. That means cardinal number is 0. So how many subsets it can have? Simply 2 raised to the power 0, which is actually 1. We know anything power 0 becomes equal to 1. So it has only one subset in it, right? So power set of A has only one subset in it. So that's the answer to the question. Now, if you want to ask me that which particular subset is this, so we can say that null subset is subset of every set. So phi is going to be there. So that's exactly the uh, set builder form, or some set builder forms into intervals. So let's see how this thing progresses. So I'm taking one example right here. So first example I'm taking is there is something, a set builder form is given x such that x is a real number, and it is given that -4 is less than x is less than equal to 5. So this set builder form, I have to write it in the form of interval. So x is less than -4, that means 4 is excluded out. So if always try to do this thing on the number line. So this is 0 here, and this is 1, this is 2, this is 3, this is 4, this is 5, and here it is going to be -1, -2, -3, -4, and so on, and 5, and so on, and -5 also. So it is up to infinity here, up to infinity here, and here x is on this particular line, which is between -4 and 5. Now between -4 and 5, but remember one thing, that x is greater than 4. That means greater than -4. That means -4 is not included. Not included. And less than equal to 5. Less than equal to. Equal to means the 5 is included in the interval. When it is not included, that boundary becomes open, and when it is included, the boundary becomes closed. So if you want to represent this entire set builder form in the form of an interval, you can write it this way, like -4, the interval is open here because it's excluded. Not included, open. 5, this boundary is included, closed. In so many books you may find it written like this. So whenever there is an equal to sign, that boundary is closed. Whenever there is a less than or greater than sign, that boundary is open. Let me take another example here. It says x such that x belongs to R. Again, x is a real number, and it is between. It is said that -12 is less than x is less than -10. So if you see, both the signs are less than, that means ni not included, that means not included. So both boundaries are going to be open. You can simply write it -12 to -10 here, and or other way around, you can simply write it -12 to -10. So on the number line, you can see here, if you keep on extending, it will be -10 somewhere, and and then it is -11 and -12 here. So it will be between -12 and 10, and both are excluded. Let's see third example here, how this example dictates. It says x such that x belongs to R, 0 is less than equal to x is less than 7. So again, you can see here, this is not included, this is included, I included. So simply this interval will be closed from the left side and open on the other side, which is 7. You can simply write it this way also, 0 and 7, and you can keep it open from this side. The fourth example, let's take one more example. X such that x belongs to R, and 3 is less than equal to x is less than equal to 4. So I think it is very clear here, both boundaries are included now, so you can simply write it 3 and 4 this way, or there is nothing open, so I think that's the best way to write it, 3 4. Let's see another example, that if an interval is given, then how possibly you can write it in a set builder form. So if let's say something like this is given, -3 and 0, and both sides are open, if it is written this way, or it is written, let's say, this way. So I know less, if the both boundaries are open, the signs are going to be either less than or more than. It is not going to be equal to sign will not appear. So it is going to be x such that x belongs to R. So you can imagine the re-engineering which is I've done on the left hand side, and -3 is less than x is less than 0. So writing an interval into a set builder form. The sixth example, I can take it as 6 and 12, both boundaries are closed. So definitely, I'm going to come up with equal to signs here. X belongs such that, okay, I'll rewrite it, x such that x belongs to R, and it is between 6 less than equal to x is less than equal to 12. Let's take one more example. It is 6 and 12. So I know it is open from one side, and x says that x is a real number, and it is open from left side, so 6 is less than x, closed on the other side, less than equal to 12. One more example, -23 and 5, and this side is open, closed, and this side is open. So both